measure things all the time, and so that's exactly what we're going to talk about right now. So measurement is what we call a quantitative observation. So when you take these 3 apples, it's kind of heavy. The word heavy is just a qualitative observation, but when you take these 3 apples and put it on a scale like this, you've converted that word heavy into a number. So in this case, we have a kitchen scale, and it tells you that it's somewhere between 600 and 800. So what we need to do is read it carefully, and then we need to assign a unit. So here we see kg. kg corresponds to kilogram. So if you're one of these students from countries where you use the metric unit, you're very familiar with this. But if you're from the United States, you're probably not as familiar with this. We use pounds here to measure these weights. A measurement has a number and a unit. There's 2 ways to measure. So when you count something, you get exactly the number of that object. So for example, I have 3 apples here. Okay, nobody can argue with me that there's 3 apples. Okay, but when you use an instrument, the number you get for the mass, maybe 650, 660 grams, that's because the instrument itself has a level of precision associated with it. Precision is just how reliable the instrument is. So some instruments are very precise. It gives you a lot of digits. So significant figures is just all the numbers that you can read from an instrument. When I say my mass is about 660, the 3 digits, 6, 6, and 0, those are what we call significant figures. They're all the digits in a measurement. Now, when you have a digital instrument like here, these are both laboratory scales, but they're different precision. You can see that when I take that same sample of copper crystals and I put it on one type of scale, the scale tells me it's 10.5 grams. When I take this and put it in an analytical balance, which is a much more expensive piece of equipment, that scale now tells me it's 10.4978 grams. This one gives me 3 digits. This one gives me 6 digits. So the one that gives you more digits is the one that is more precise. Anything that has more significant figures is more precise. So this guy has 6 significant figures. This guy has 3 significant figures. What happens when you have a ruler? You have to read the number yourself. These are what we call analog instruments. So you got to follow these steps to read your measurement. The first thing is just to figure out what is the size of these little marks right here. The way we do that is we just take the difference between the 2 written numbers and divide it by 10. I would say the majority of instruments have 10. So like this ruler, for example, so you can take difference of any 2 neighboring numbers. So 1, and then divide it by the number of marks. Well, as I said earlier, there's 10 different marks. 1 divided by 10 is 1/10 or 0.1. So when I read this, I would say this is 1. The next one is 1.1. The next one is 1.2, etc. The unit is centimeter. How do I know? Because the ruler shows me centimeter. So this is 1.1 centimeter, 1.2, and so on. Let's say I'm interested in measuring a line that I draw from the beginning of the ruler all the way to the point where B is. What is the length of that line? Well, the next step after you figure out the size of those increments is you find the 2 numbers that flank the measure mark. B is right here. It's slightly before that longer mark. So I find between 1.4 and 1.5. This is a little bit longer than 1.4. So this is what you have to do next. You have to add 1 more digit as an estimate. What is your guess? Because we say it's 1.4 something. A lot of times people would just choose the middle number, which is 5. So they would say 1.45. You can say it's 1.48 centimeter. And that would be the value of the length of a line that's drawn from the beginning of the ruler all the way to B. Here are some other examples of reading instruments.
So I'll walk through a couple of these. So for example, let's take a look at the first one. This is a really common type of instrument that we call a graduated cylinder. This is a common glassware we use to measure liquid volume. The number goes from small at the bottom, bigger at the top. But when you look at a liquid in a glassware, it forms this curved shape right here. And so the meniscus is the lowest part of that curve, which is right here. So in this particular reading, it's right there, okay? That's where the meniscus is. I have to determine the size of the marks. Remember, that's step 1. And to do that, I'll take the 2 numbers that are neighboring to each other, 7 minus 6 divided by 10, because there's 10 marks. So each one of the little marks is 0.1 milliliter. So we start with 6. This is 6.1, 6.2, 6.3, 6.4. 6.5 is a longer one. And look at 6.6. So the volume then then it's going to be 6.6, and then the unit is milliliter. Now, you might say that, okay, that's it, I'm done. It's exactly at 6.6, but be careful, because remember what I said earlier, you always have to add one digit as your estimate. In the example that we looked at earlier, the estimate was either a 5 or an 8, because the length of that line is between two digits. But in this case, exactly on the 6, you would just say that your estimate is 0. So you would put 0 right here. So these two digits right here is what we call our certain digits, and that's because we read it from the glassware itself. And then the 0 is what we call our estimated digits. It's not 6.58, it's not 6.62, it's 6.60. Let's take a look at the thermometer here. Okay, so you can see that this is the 37. So the liquid is right here. So you're going to have to figure out what is the size of the mark is. It's going to be 0.1 in this case because there's 37, 38. We subtract those two together, divide by 10, we get 0.1. So right now the liquid is at 37.1. We're not given the actual units, so I'm just basing it on typical thermometer. Don't just write 37.1. You have to add one estimated digits. Again, these three are your certain digits, and you need one more. If you think that it ends exactly at that 0.1, then you would say the estimated digit is 0. So 37.10 degrees Celsius is the correct way of reading this thermometer. Okay, so hopefully that helps you understand how to read this analog instrument. And if you have any questions, feel free to contact me.
I said that in these two balances, the one that has more significant figures, that one is the more precise instrument. It just gives you more digits, which means more information. You know the mass of the sample to a higher precision. As a result of that, it's really important to know how to count the number of significant figures. In examples like this, I just counted all the digits that I have. 3 digits here, there's 3 significant figures. 6 different digits there, that's 6 significant figures. Things are not always that simple. So let's look at the rules for counting significant figures. Everything that is non-zero is counted. 2.35 has 3 significant figures. They don't all have to be different digits, by the way. If this is 2.33, it still has 3 significant figures. The zeros are the part that sometimes might be confusing. First off, interior zeros. Okay, these are zeros that are between two non-zero numbers. Those are automatically counted as significant. So if I am given this number, I would say there's 5 significant figures. Trailing zeros are zeros that come after some non-zero numbers. So zeros to the right. For this ones, you gotta be a little careful. It depends on whether the number has a decimal point or not. If it has a decimal point, you will count those zeros as significant. So for example, if you have a number 5.400, this number has 4 significant figures. Now, sometimes you don't have that. So for example, you have the 350. So there's 3, 5, and 0. So you might say, okay, there's 3 sig figs there. It's not really clear because that 0, some instrument that is an estimated read, sometimes it's not. So when we write something like this, we don't really know if it has 2 or 3 significant figures. To make it less confusing, we would write it as scientific notation, which is something that looks like this. 350 is the same as 3.5 times 100, or 3.5 times 10 to the power of 2. So I can write the 3.5 as 3.5, or I can write it as 3.50. But if I take 3.5 times 10 to the second and put it in my calculator, I get 350. If I take 3.50 and multiply it by 10 to the second, I also get 350. So both of these writings, 3.50 times 10 to the second and 3.5 times 10 to the second, give me 350, but the number of significant figures is different because in this case, that's 2 sig fig, whereas here I say 3 sig fig. Why is that 0 significant? Because it comes after a decimal point. When we want to avoid confusion with the number 350, if it's only a 2 sig fig number, then we would write it as this. If it's a 3 sig fig number, we would write it like this. Now here's another trailing 0 situation. Trailing 0 that fall before a decimal point. Okay, so again, if you have a decimal, then you always count it. So for example here, 50.0. The ones that are after the decimal point is significant. What about the 0 in the middle? Well, you can think of that 0 in the middle as being between 2 significant figures. So therefore that third one must also be significant. So 50.0 would have 3 significant figures. All right, last 0 to talk about are what we call leading zeros. Zeros to the left of non-zero numbers. They are not significant. So for example, if I have the number 0.0005, they are leading zeros. They come before the 5. So all these are not significant. All right, so here's some examples on how to count significant figures. I just said that this number that are ambiguous a lot of times needs to be written in what we call scientific notation. What is scientific notation? It's just a way of writing really small or really large numbers by using powers of 10, because it's a more compact way of writing the numbers, and it's a lot easier for people to see how small or how big that number is. So here's a number. It's really hard for me to know how small this number is. Is there like 7 zeros there or like 10 zeros there? I can't really tell. But if I write it this way, it makes it really obvious that there is 9 zeros that come before the 1. Because I look at this exponent right here, it's 10 to the minus 10, so that means there's 9 that comes before its count. So 1, 2, 3, 4, 5, 6, 7, 8, 9. And then the 1 shows up, okay? So that, in fact, is how you want to write really small or really large numbers. You count so that you get something times 10 to the power of something else. That number that you write, the decimal part, has to be between 1 to 10, okay? So like in this case, 1.2, so that's between 1 to 10. For like a number like this, my goal is to move the decimal point until I get to that number, right? That's between 1 and 10. Right now, the decimal point is right here, right where my cursor is. So I'm going to move it 1, 2, 3, 4, 5, 6, 7, 8, 9. And look, if I stop the decimal here, my number would be 0.12. That's still not between 1 and 10, right? So I got to move one more. I move one more, so that's 10 steps. So when you're dealing with numbers that are smaller than 1, your exponent is negative. So in this case, I would write 1.2 times 10 to the power of negative. That was 10 steps to get from that decimal all the way to 1 right here. So that's why it's 10 to the minus 10. If I write a number like 10 to the minus 4, it just means that it's the same as 1 divided by 10 to the 4th, 10 to the 4th being 10 times 10 times 10 times 10, or 10,000. So it's like taking the number 1, dividing it 10,000 times. Or if you want more visual examples, you take an apple and you divide it 10,000 times. You can imagine how small that piece of apple would be, right? A positive exponent just means that the 10 is multiplied by n times, whatever the exponent that is. So for example, if it's 10 to the 3, that just means 10 times 10 times 10, or 1,000, okay? So here's an example of a large number, 5,983. We want to write it as scientific notation, and we're going to move it back, right? So 1, 2, 3. Now why stop there? Because when I write it here, it becomes 5.9. 5.9 is between 1 and 10. I would write 5.983, and this is a big number, so big number is a number that's bigger than 1. It's a positive exponent. I move 3 steps back, 10 to the 3rd. That's all you need to know about positive and negative exponents. Using scientific notation is one method. Another thing is to use what we call metric unit and prefixes. And some of you are taking this class from countries where you are using metric units already, but in the United States, we don't use that. So I'm going to talk a little bit about some of the common metric unit that we use. So for example, you see this unit meter, use that to measure length. We have the unit kilogram, has the symbol kg. That's used to measure mass, so meter is m. And then we have second for time, symbol s. You'll see a temperature measurement with the unit Kelvin. Of course, typically what you'll see is either Celsius or Fahrenheit, but Kelvin is the one we use for scientific measurements. How you use the metric unit, it depends on the size of the numbers. We have these different prefixes. So in this case, these metric prefixes are things that we attach to the beginning of the unit. Let's say we have the length of bacterial cell is 0.000, 5 zeros. Now, if I want to write this as scientific notation, what would I do? I would move it one more here, right? So it's between 1 to 10. And I would say, okay, it's 1.22. Since this is a small number, I need a negative exponent. 1.22 times 10 to the minus 6 meter. You can also use the metric prefix, because metric prefixes is just like scientific notation. It gives you different powers, but then the powers have different names to them. So when we did 10 to the minus 6, so you scan through this table of metric prefix, and you find that 10 to the minus 6 is the same as micro. So then, instead of writing 1.22 times 10 to the minus 6, I can just say it's 1.22 micrometer. Micro, the symbol for it is this Greek letter M. So I would use that. So that's 1.22 micrometer. Sometimes people would use this word too, 1.22 micron. What you need to know in this class is to write it this way if you are asked to convert it into a metric prefix. There's another question here. For a really large number, you want to express this in units of mm, that's mega, 10 to the 6. So how do we express this in 10 to the 6? It would go 1, 2, 3, 4, 5, 6. You're not moving it all the way to the 4, but you're moving one step less, right? So that means it's going to be 40.075 times 10 to the 6 meter. Or another way to write that is just 40.075, as we said earlier, mega meter. Hopefully that makes sense. Happy to answer any other questions you guys might have.